Hello and welcome to our GCSE Chemistry Electrolysis workshop. Quite a few people have been asking about this topic and we thought we'd produce a video such as this one to hopefully make life a little bit easier for you. All the slides will be available for you to download at the very end as well, and if there's anything else that you need to clarify, then you can always get in touch with us. So let's dive straight into it. Firstly, when I talk about electrolysis, I like to ask why. Why do we do this thing called electrolysis? It's always a useful question to ask. And it's always important to know the answer to that question. And really the reason for that is that certain metals, such as copper and aluminium, are discovered on Earth as oxides. In other words, they've already reacted with something in the air or something in the atmosphere. So, for example, copper oxide or aluminium oxide. And that, unfortunately, is not helpful. Compounds don't have the same properties as the separate elements. So, for example, copper conducts electricity and we use it in wires, but copper oxide does not. So, what we like to do is separate these compounds back to what they were originally. So, for example, get copper oxide and aluminium oxide back to copper and oxygen, or aluminium and oxygen. Let's talk about how we do that. Now, before we can go dive into electrolysis, we have to talk a little bit about displacement reactions. Because electrolysis is expensive and it requires a lot of energy. So we don't want to use electrolysis in every situation to separate every single compound. I mean, as the name suggests, it requires electricity. Electricity is not free. So let's first go into displacement reactions because they are a cheaper alternative. But unfortunately, they only work with elements that are not very reactive. So usually we can only separate an element from, let's say, oxygen if the element is less reactive than carbon. So I'm going to show you now a reactivity series bouncing in. The reactivity series, as you may have seen before, is a list of elements on the periodic table in order of reactivity. And as you can see here, if we just highlight this particular part here, that these elements up here, they are extracted using electrolysis. So if we have sodium chloride or potassium oxide, for example, we tend to use electrolysis for those. For the elements below carbon, like zinc, iron, we will be able to extract them using carbon, and we're going to show you how that works now. So just so you understand, we use displacement for extracting elements that are generally less reactive than carbon, but we use electrolysis further up the chain because it becomes harder and harder to extract those using displacement reaction. We'd love to do that, but it becomes harder and harder to do that. So let's move on and talk about some specific displacement reactions. So as you can see here, if you place iron in a solution of copper 2 sulphate solution, then because iron, as we saw in the previous one, is more reactive than copper, what it does is it kicks the copper out, as we can see here, and becomes iron sulphate, leaving us with copper separately. So the iron has kicked out the copper, becoming iron sulphate, and we have extracted the copper from copper sulphate. We've got the copper that we needed. If we do another one of those, then zinc here with iron sulphate, because zinc is more reactive than iron, if we go back to the periodic table I'll be able to show you, zinc is more reactive than iron, and so zinc kicks the iron out, zinc sulphate, and we have iron left. And so that is, in a nutshell, displacement reaction. So if we can use displacement, it is a much easier way to do it, mainly because if I want to extract copper from copper sulphate, then iron is quite readily available, and we can find iron and we can react it with it and kick the copper out. So it's quite a nice, cheap, easy way to extract copper from something, or to extract iron in this case. It is much easier to do it this way. Let's move on to electrolysis now. The best way to understand electrolysis, and particularly half equations as we're going to see later, is to try to go back a little bit and understand ionic bonding. Now, I'm going to do that now. So, for example, copper atom looks like this. The copper ion looks like this. Now, how did the copper atom become a copper ion. Because it's a 2+ ion, it's positively charged by 2. It means that it did that by losing 2 electrons. Important to understand that, because if I want to go back from copper 2+ back to copper, then I would do the opposite. I'd need to gain those 2 electrons back. Important to understand that. Let's do another one. Oxygen as an atom is just O. The oxygen ion is O2-. How did oxygen become O2-? It did it by gaining 2 electrons. So if I've got an oxygen ion that needs to go back to being oxygen, it would need to lose those 2 electrons to get back to being oxygen. If we do one more example, bromine as an atom is Br. As an ion, it is Br-, which means how did it go from being bromine to Br-? It gained 1 electron. So again, if I want to go back from this ion to going back to being bromine, then I would need to lose that 1 extra electron that I have just gained. Remember that, because if you can understand how we go from an atom to an ion, and therefore an ion back to an atom, it will make the half equations that we do later much, much easier. So, let's talk a bit more detail about electrolysis now. Firstly, electrolysis only works with solutions, in other words, something dissolved in water, or with molten substances. The solution must be in liquid form so that the ions can move and conduct electricity from one side to the other. I will draw an electrolysis diagram in just a moment. There are 2 electrodes, the anode and the cathode. Try and remember that the anode is positive and the cathode is negative, but hopefully you won't need to worry about that. They're all connected to a power supply and then inserted into the solution. So for example, if I do a very rough diagram here, you will have the solution. So that might be melted copper oxide or melted aluminium oxide, as we'll see later, or sodium chloride in water, a solution of some sort. We then have these 2 electrodes going into there, and they are joined together with a battery, so we have a power supply there. One of these electrodes is positive, one of them is negative, and we have electricity being conducted from one side to the other here. That is why electrolysis works, because this solution conducts electricity. Let's now talk about a specific electrolysis that you need to be aware of. So, the electrolysis of lead bromide is what we're going to do. Before I go into too much detail here, I'm going to talk about how lead and bromine actually became what lead bromide is. Lead bromide is PbBr2. Now, let's just briefly understand that. We will have had lead ions. Now, lead ions are Pb2+, and we will have had bromine ions, which are Br-. So, how did we get from lead ions and bromide ions to PbBr2? Well, the lead atom, as we saw earlier, must have lost 2 electrons to end up being there, and the bromine must have gained an electron to go to being there. Now, there's going to be 2 bromide ions, which we'll again talk about in just a moment. So, first of all, lead bromide is an ionic compound. So when it is molten, it will conduct electricity. Electrolysis of lead bromide breaks it down into lead and bromine. Remember, the whole purpose of doing electrolysis is to separate the compound. So if your compound here is PbBr2, we want to get back to lead and back to bromine ideally. And here's the electrolysis of lead bromide. Let's just briefly talk about this. So as you can see here, we have, when we put this into solution, or when we melt it in this case, we end up with positive lead ions and negative bromine ions. The reason we have this whole liquid situation is because now the ions are separated again and they can move to different places. The positive ions move to the negative electrode, as should be obvious, the opposites attract. And the negative bromine ions move to the positive electrode. So we have done the electrolysis there. They have been separated. Lead forms over here. As you can see down here, there's a bit of lead falling off. And bromine comes off as a gas over here. And so again, that is the electrolysis of lead bromide, because we have separated the lead and the bromine. They were a compound, lead bromide, and they have now gone back to being lead and bromine. As always, the complicated part of this entire topic is the half equations. Let's move on to talking about the half equations. Now, as many of you know, half equations can be quite complicated. Okay? However, if you have understood what we talked about earlier, about ions and atoms and how you go from atoms to ions and ions to atoms, this should be easier, because in this electrolysis that we just saw, there are Pb2 plus ions that turn back into Pb. Remember, that is the entire point of the electrolysis, to get the ion back into being the original thing that we wanted, or to turn the compound back into the original thing. So we've got these lead ions floating around in the solution. We want them to go back to being lead. Now, how would they do that? Well, how did lead, or Pb, become Pb2 plus in the first place? It became Pb2 plus by losing 2 electrons. That made it a positive ion. Now it needs to gain those 2 electrons back, and that is the half equation. That we have a Pb2 plus ion, it has to gain 2 electrons, and it goes back to being Pb. And that is what happens at the negative electrode. There are 2 separate equations here, 2 half equations, because one's at the positive electrode, one's at the negative electrode. At the positive electrode, we have bromine ions, or bromide ions, and they eventually turn into bromine. Now, the complication here is that bromine, like many other gases, comes in pairs, and so we have a Br2 actually there, and we have to balance it with 2 bromine ions there. Now, how does a single bromine ion go back to being bromine? How did bromine become a bromine ion in the first place? It gained an electron. So now it needs to lose that electrons. But because just to balance everything, it needs to lose 2 electrons. And that is the half equation that you have at the positive electrode. Where people get confused about all this is that they, in textbooks and in schools sometimes, they will sometimes write that second equation like this. They will sometimes write it like this. They will say 2Br minus gives Br2 plus 2E minus. So they will move the negative to the other side. Just, it's a presentational thing, because I think they don't like having negatives in a chemical equation. You generally have something plus something gives something plus something else, so they prefer not to have that. But what it does mean is that if you see this, it looks a lot more confusing than the first one that I did. So my recommendation is, and I know that I've seen exam mark schemes and everything works fine, remember this one here, and it makes a lot more sense if you understand it, that, well, how did bromine, a negative bromine ion, the way it became back to bromine is by losing 2 electrons. And another little tip about all of this is that whatever the sign here is, so if you've got a positive ion, it will gain electrons to go back to being what it was. If you've got a negative ion here, it will lose electrons to go back to being the original atom. So if you want the textbook summary of the half equations, then you can have it here. It explains the steps that you'd go through to get from Pb2 plus to Pb. It explains it in a little bit of detail. I thought I'd put it into the slides, but I think my sort of verbal explanation should be better. And similarly, at the positive electrode, you can see what goes on there to go from a negative bromine ion back to bromine. And as you can see, that is exactly what we talked about over there. So that's the one that I've written first, which I would recommend. They've essentially started with that one. So there are specific electrolysis examples that you need to be aware of. And the one we're going to talk about now is the electrolysis of aluminium oxide. I'm not going to draw any of this. I'm just going to talk through it because, as I say, most people can realize what happens here when I tell them this. Aluminium forms an Al3+ ion, and oxygen forms an O2- ion. So therefore, when I melt aluminium oxide, because it needs to be molten, remember, for the electrolysis to happen, the positive ions will go to the negative electrode, and the negative ions will go to the positive electrode. So that much most people get right. Okay, we know that aluminium will form at the negative electrode, oxygen will form at the positive electrode. But can you get the half equations? And you should be able to now, because if I go to, so if we say the negative electrode, I've got aluminium 3+ at this electrode. It needs to end up being back to aluminium, right? We know that that's what's going to happen. It's going to form aluminium again. We should know now how to complete this half equation. It's going to have to gain 3 electrons to go back to being aluminium. There's your half equation. Let's do the positive electrode. There we have O2- ions, and they will eventually go back to being oxygen. Again, the only complication with these gases is that they're written as 2s. So we have O2 there. So firstly, I need to balance this. So I need to put a 2 over here to get 2 oxygens and 2 oxygen on that side. Now, how does an O2- ion go back to being oxygen? It will lose 2 electrons. However, because we've got 2 ions now over here, we need to make this a 4, and that is the half equation there. Once you've understood what I'm doing here, all half equations scenarios should make sense, okay? Generally, the negative one is easier because it kind of always follows the same format, this one over here. But, as I say, with a bit of practice, the other one should also make sense. So, that is electrolysis of aluminium oxide, and that works for any compound that we melt to do the electrolysis. What's next, though, is electrolysis of aqueous solutions, and as we're about to see in capital letters, this is different. Firstly, aqueous means that dissolved in water, okay? So far, the compounds that we've used in electrolysis, like in the lead bromide example and the aluminium oxide example, the compounds were molten. We melted it, right? Which meant there were only 2 ions present in the solution. In the aluminium oxide ones, there was Al3+ and O2-. In the lead bromide ones, there was lead ions and there were bromine ions. They were the only 2 ions. So it made it quite simple as to what was going to happen. This time, because the compound is dissolved in water, we also have water, which means that we also have H+ and OH- ions to contend with. They are also inside the solution, and we have to determine which one will go to the electrode, because now we've got 2 positive ions, the H+ and something else, and 2 negative ions, the OH- and something else. So, which one, however, goes to the electrode? Which ion? We have 2 positive ions and 2 negative ions, and now we're going to explain how that works. I'm going to do an example after this to make this make sense. At the moment, I just want to tell you the theory. At the negative electrode, you will always have hydrogen ions, as we just saw, because there will be the H+ ions from the water and one other positive ion. So, for example, I don't know, we're going to see sodium in a little while. There'll be H+ and Na+, 2 ions. Now, to determine which one of those 2 goes to the negative electrode, they can't both go to the negative electrode. Only one will go. The less reactive one goes to the electrode. Okay, so in the example of, if we say H+ and Na+, because that's the example we're about to do, in that particular scenario, H is less reactive than sodium. Sodium is very reactive, it's in group 1. And so hydrogen is less reactive than sodium, and that goes to the electrode. So that's how you determine it's the less reactive one of the 2 positive ions that goes to the electrode. So what about the negative side? So at the positive electrode, where the negative ions go, there will be OH- ions and something else. So in the chlorine example that we're going to do, the sodium chloride example, there will be Cl- ions there as well. If the other ion is a what we call a halide ion, so Cl minus or Br minus or I minus, as we sort of saw, then that's the one that goes to the electrode. So in this particular scenario, when there's Cl minus and OH minus, the Cl will go to the electrode because it's one of those group 7 halide ions. If not, if there's something else in there, then the OH minus ions will go to the electrode. Now this will all make more sense when I show you the electrolysis of sodium chloride solution. So sodium chloride solution, let's have a look at the picture of it bouncing in again. We have got sodium ions. Let's focus on these. So we can see sodium ions there. We can see hydrogen ions there. And as you can see, the hydrogen ions have gone to the negative electrode. The sodium ions stay there. Okay? And the chlorine ions go instead of the OH minus, because chlorine, as I say, whenever we have these halide ions with OH minus, they're the ones that go. So we end up with hydrogen gas coming off over here and chlorine gas coming over here, and we're left with Na plus and OH minus ions in the solution. They just stay there. Nothing happens to them. Hydrogen is less reactive than sodium, so hydrogen is what's formed at the negative electrode, not the sodium. And on the other side, because there are chloride ions here, they're the ones that form at the positive electrode instead of the OH minus ions. As always, we need to talk about the half equations. As you can see, a solution of sodium chloride contains Na plus, Cl minus, OH minus, and H plus ions. Now, sodium is more reactive than hydrogen, and so that's the one that so hydrogen is the one that's formed at the negative electrode, and there's your half equation for it, which now you should be at a point where you can form that yourself. Okay, and there's your half equation for chlorine. And again, what makes more sense is if you write it like this. So we had a chlorine ion. We need to put a 2 in front of it because we've got a 2 over here. A chlorine ion loses an electron to go back to being chlorine, and so 2 chlorine ions, as we've got here, will need to lose 2 electrons to get back to being chlorine. Similarly, over here we had hydrogen gas, which is a 2, and that's why everything's got a 2 in front of it. Lastly, we will do the electrolysis of copper sulphate solution. And here is the diagram for the electrolysis of copper sulphate solution. Let's just talk about what's in here first. So we have copper ions, 2+. We have H plus ions because of the word solution. We have got OH minus ions again because of the solution, and we have these sulfate ions, which are SO4 2-. Now, on the positive side, as I say, the less reactive ion goes to the electrode, and in this case copper has gone to the electrode because it is less reactive than hydrogen. Hydrogen stays in the solution, so we've got copper forming over here. Great. On the other side we have hydroxide and sulfate ions, and as I said to you, in this case the OH minus ions go there because the other ion is not one of those halide ions. It's not chlorine or bromine or iodine or anything like that, and so OH minus ions are the ones that go there. And that leaves us, lastly, with the half equations in this one. And these are probably the most complicated ones to deal with. So let's talk about those. At the negative electrode, let's write that down over here. That's where we've got those copper ions going. As I said, the copper ions have gone there because they're less reactive than the hydrogen. They get there and gain 2 electrons to go back to being copper. That's the easy one. This one is probably the most complicated one so far, just because the balancing is a little bit more complicated. At the positive electrode, we showed OH minus ions going there. Now, OH minus ions, when they go to an electrode, they become water and oxygen. Okay, so they become water and oxygen. Now, what we need to do first is balance all of this. Now, to balance this, I'll do it reasonably quickly, but to balance this, we put a 2 here, so we've got 4 hydrogens on the right, and now 4 oxygens on the right as well, and then we put a 4 over here to get everything balanced. So that's now balanced. Now we've got 4 hydroxide ions. How did a hydroxide ion become that in the first place? It must have gained an electron, so now it's going to lose that electron, but because there's 4 of them, it needs to lose 4 electrons. So they are the half equations at the positive and negative electrode for this particular electrolysis. And this explains that in nice typed writing. So you can see exactly what they've done, why they've done it, and hopefully now that electrolysis makes sense. Now, just to sum up, you might get these specific electrolysis experiments that we've talked about. You might get one that you've never heard of, but the principle remains the same. Your positive ions go to the negative electrode, your negative ions go to the positive electrode, and if you've got solution, in which case you've got hydrogen and OH minus ions in there as well, then on the positive side, the less reactive one goes to the electrode, and out of the negative ions, the OH minus goes there unless the other ion is a chlorine or a bromine or an iodine. That is the rule. You've got to try and remember those rules. You've got them in these slides. Now, finally, we can talk about oxidation and reduction. This is the sort of higher level part of this topic. Now, in every single electrolysis reaction that we've seen so far, something gets what we say oxidized and something gets reduced. All you need to know for this is the acronym OIL rig, where oxidation is the loss of electrons, oil, and reduction is the gain, that's the rig. Important to remember that this acronym is for of electrons. So oxidation is the loss of electrons, reduction is the gain of electrons, not anything else. And so what we can do now is just have a look again at the other half equations we've seen so far. In all of the half equations so far, one of the ions was always gaining electrons. That's why we put plus something E minus. And the other ion was losing electrons. We put something minus E minus, which makes it clear which one was being oxidized, which one was being reduced using oil rig. So if we just go back to what I wrote before, here we can see that electrons are being added, right? So that's a gain of electron, which means that what's happening here is reduction. We say that the copper, in this case the copper sulphate is being reduced, and at the positive electrode over here, electrons are being lost, and therefore that is oxidation. Oxidation is the loss of electrons. And that is all you really need for these questions. Most of the time you will get asked what is happening at the negative electrode, or how do we know that oxidation is taking place? It's because it is the loss of an electron. How do we know that reduction is taking place? It's the gain of electrons. No, remembering oil rig is generally all you need to be able to correctly answer questions on this topic. Otherwise, thank you very much for watching. Please do let us know if there are any other topics that you want explaining, and give us some feedback about the video that you've just seen as well. Thank you.